started, so good, we're rolling. All right, we'll start recording here. All right, so today is I'm giving a special lecture today on pervasive computing, Internet of Things, and smart buildings. So just a brief introduction. So my name is Jeremy Gummison, so I'm a research scientist here in the College of Information and Computer Sciences. So I spent a few years in industry working at a couple different places before I came here in a research role. So I was at HP Labs, and then I was at Disney Research. At both those places, so I kind of had a role in some innovations related to wearables and Internet of Things technologies, and we'll be talking about one of those projects like during the second half of this lecture, and during the first half it'll be more of a sort of a traditional course-like material that like Prashant probably would have presented. So the first slide here I want to go over, so what exactly is pervasive computing? So pervasive computing, another name of it could be ubiquitous computing, and what that basically means, they're computers that sort of disappear into our environment. So, maybe you could think of a form of pervasive computing being, like a wearable, or like an Apple Watch, right? Or maybe even like a phone, right, is more pervasive than it used to be. But these are even like really small sensors, right? They could be even like down to the size of a grain of sand. And one of these computers, it might contain a processing element, so like a low power version of a processor you would find in a laptop. It'll contain some kind of sensing, so it can collect information about the environment. And then finally, it'll have some kind of radio, right? So it needs to have some way to take that information it collected and send it back to where we can see it. And so some applications of pervasive computing that we're seeing, so there's smart health, so there's smart buildings. So these could be applications where maybe we're trying to optimize the power of a smart home, right, by adjusting things like heating and air conditioning based on environmental factors. So smart transportation. So I think the Tesla is a big example of how far we can push sort of smart vehicles, where we're seeing cars that can sort of do sort of adaptive lane changes, adaptive cruise control, and then eventually the roads themselves will be part of sort of this infrastructure of optimizing transportation. And then the last is smart agriculture, right? So there's a lot of people that live on Earth. And we can use some of this technology to do a better job in feeding them, right? So if we have a lot of fine-grained information about the environment, so say for example, we know soil moisture, so sort of at a very high spatial resolution, we can do things like water crops more efficiently, so we're not overwatering one area or underwatering another, and then the same goes for nutrition. And then that, so basically soil nutrients, right? So some of the plants might not be getting enough fertilizer, while others might be over-fertilized. So you can basically close sort of this feedback loop where we're collecting sensor information, and then we're optimizing the way that we deliver these resources to agriculture. So what has made sort of the rise of pervasive computing possible? Well, so the first is miniaturization of computing, right? So there's this thing called Moore's Law that was going on for many years. I think now it's dead is the official verdict, but basically, this allowed us to both increase the amount of transistors we could put on a CPU, and also at the same time we're making them lower power, right, by reducing the supply voltage we need to run them. And then the second part of the equation, right, is basically making the sensors themselves more power efficient, right? So there's a whole class of sensors called microelectromechanical systems. So basically, what this means is they've taken what used to be sort of like an accelerometer used to be sort of like a large cylinder that you would use to sort of measure, acceleration amongst three axes. And now they've taken the basic functionality of an accelerometer and fit it, inside of a chip that's, smaller than the size of your fingernail. And so that's enabled us, to put these sensors and, really small sensors you can deploy in the environment. And also, there's a whole bunch of these that are in your mobile phone, and, it's probably something that everybody even takes for granted now. And so, of course, this has given rise to the Internet of Things, right? So we can think of physical devices themselves being networked entities, right? So it's not just laptops and smartphones. So now you can actually have like a refrigerator that not only has a physical presence, right, but it also has sort of a virtual presence on a network. So one of the big areas of growth, so sort of in the last 5 years or so, are a bunch of applications related to smart health. So some early example of wearable devices that have gone after this. So there's an early, I guess that's a Windows-based smartwatch, which isn't around anymore. But of course the the Fitbit is also still a very popular fitness device, and they let us track things, like the number of footsteps you've had per day, what your sleep quality looked like over time. And then of course, there's new technologies that are emerging, right? So these, small sensors that we put on our wrists are just sort of the beginning of what's possible. So on the left, so this sleeve sensor here, this is actually a research project that I was involved with. So what this is it's called a triboelectric joint motion sensor. So this was a collaboration with the Department of Chemistry, and basically what this lets you do is, so there's two fabric layers there that basically have different surface charge potentials, and when you basically move your arm, these two textiles will rub against each other, and you can measure a voltage potential across them, and you can convert so sort of those signals that you get into things like what direction you're moving your arm or how fast you're moving it. And so the big advantage over doing things with smart clothing versus something rigid like a wristwatch is you can think of being able to incorporate sensors all over the entire human body without restricting motion or having like a million batteries that are placed all over your body that you would each need to recharge. And then on the right, so you all probably remember Google Glass. It's not really around anymore in sort of the consumer space, but this is another prototype. Basically a prototype computational eyeglass that was built in the sensors lab here at UMass. And so the purpose of this is there's a very low power grayscale camera. So I think it had a resolution of maybe 100 pixels by 100 pixels. And so because it doesn't have high resolution and you're only looking at like a monochrome image, you can actually sort of continuously capture images of the eye over time. And specifically what we were after was looking at the location of someone's pupil, right? So this has like a number of applications. So like I guess if you want to sell people things, right, you could like maybe figure out what product someone is looking at on a shelf. Or for medical applications, there's a lot of neurological disorders that you can sort of get a good grasp on how they're progressing based on the way that eye movement changes over time. So just in terms of a health platform, this is all really useful. And so if you're really smart about the way that you sort of merge the sensing, computation, and communication elements of a device like this. So this actually can run continuously for more than a day if you're really careful about how you use the sensor. And then another example of sort of pervasive computing, so smart buildings. So everyone's probably familiar with smart thermostats at this point, right? So smart thermostats can basically figure out when you're home versus when you're not home, and figure out how to schedule, when to turn on heating and air conditioning, corresponding to human presence. And also it can do things like, it can look across, the next couple weeks of weather forecasting and basically kind of figure out, when is the most opportune time to use heating resources. And then, so sort of smart plugs, smart appliances, and smart locks are all other examples. So smart plugs, right, you can basically use these to disable. So if you leave, so sort of like even like a lamp with like a dimmer switch, if you leave that plugged into an outlet, it turns out that it actually is drawing power over time even though you're not using it. And so these smart plugs can actually be actuated sort of by a centralized controller in your home, and it can get rid of some of this idle power consumption. It could do things like turn on or off your lighting at a more intelligent time. And then so other smart appliances like fridges, right? So you have like a on the touch display there, I believe that's a prototype smart fridge from Samsung. And you can sort of, maybe it can figure out what items in your fridge are about to expire or what you need to throw out, automatically figure out what food items you should buy for the next week based on what you have left. And then sort of, so these are all things that sense your environment, but the last, right, are sort of these things that can actually sort of directly help us in the terms of and it's sort of, you can think of it as helping us in terms of sort of cognitive assistance, right? So they're basically things that you would like to know that you don't know, and now with sort of these smart speakers like the Google Home or the Amazon Alexa, you can basically just ask it questions and it'll give you answers, and you don't even have to go to your computer anymore. Okay, and then this is the last sort of example of classes of pervasive computing I'm going to talk about. So this is smart transportation. So the Tesla is like sort of an example of like a smart car, right? It does a lot of things intelligently and can figure out how to get you from point A to point B without running out of batteries, right? So it can dynamically sort of change the route that you're going to take, based on environmental conditions. And but building on smart cars like the Tesla, so we can actually make the roadways themselves smart. So the example that's shown in the picture here, so this is sort of reactive lighting. So say if a car has a radio, right, and it can sort of beacon its presence, and then a light, could know that a car is approaching before it's actually reached a location. So instead of having all of the street lights, on all the time at night, right, you could basically turn them on, ahead of when a car is going to arrive, at a certain segment of road, and you could save a lot of money in terms of the electricity that you would spend on the lighting. And then just overall the concept of connected cars, right? So you could think that maybe this is already solved, right? Because a lot of cars have an internet connection, but actually it turns out that sort of the latency between having a car talk to some server in the cloud and then getting a response back, so that latency could actually be long enough that maybe you don't get an alert that you're about to have a collision in time to stop it. So it's sort of an active area of work, right, is on how we can actually have peer-to-peer network connections between vehicles, right? So that way, if your car was about to, we're getting a little bit too close to the car in front of you because you're sending out these wireless beacons that might contain sensor information, you could, directly deliver a message to that car, in front of you to prevent an issue from happening. So everything that I talked about here, you could probably think of some example of a smart application that would go with sort of the sensing hardware, right? And so the way this works, right, in a typical sort of health device, like here we have a Fitbit, and it talks to the phone, which talks to the cloud. So usually the way that these will work, right, is the wearable device has a sensor, it's continually sensing stuff. It may or may not have a connection to the phone, persistently, right? So when it does have a connection to the phone, basically the wearable device sort of has a queue of sensor readings that it wants to send to the phone. Once you get it to the phone, then usually what's done now, right, is so sort of like Fitbit or Apple will have their own database that resides in the cloud where all of the information sort of gets archived. And then there might be an analytics engine that runs in the cloud to actually look at all of these raw sensor readings and try and figure out something meaningful about them, right? So you might look at acceleration values over time and translate those into footsteps, for example. Or it could be heart rate, like maybe you want to know heart rate variability over time, right? To understand, if maybe you have a heart condition. So the cloud can help with those analytics. And then usually, there's some form of a dashboard that you can log into on your website, or it could be in a mobile app. So basically the results of all of this analysis get pushed back to the phone. And then, so environmental sensors, so they also connect to the cloud. So one other aspect of these, right, so a wearable will usually use something like Bluetooth or Bluetooth Low Energy, right, because that's a radio that's built into your phone. So environmental sensors, they do a very similar thing, but they will either talk directly to an access point, right, so if basically the embedded sensor in your home has Wi-Fi, it can directly talk to the internet, through your Wi-Fi router. But here, this is an example of sort of a wireless hub. I know this is required for a device like the Philips Hue light bulb, right? It needs to have basically this gateway device, because I think the Hue bulbs use sort of a version of a protocol called Zigbee. And so that's different from Wi-Fi in that it's basically more power efficient, right? And it sends smaller amounts of data. So there's a bunch of radios that exist, right, that are sort of optimized for some of these like constrained sensing devices. Yeah.
So on the previous slide with the smart highways and the connected cars,
yeah,
where are there research problems here? Because it seems like I could implement these with just existing technology.
Yeah. So I've kind of reviewed some papers on this over the years. So one that I looked at recently was looking at this sort of as a CDN type issues. That's a basically figuring out, right, how to automatically sort of index information. So basically you have a car, right, and maybe you have like a dash camera, and you have information that you just recently detected from your car. And so because you don't necessarily have the amount, the time required to sort of send this to the cloud, have it do the learning, and maybe it tells you, oh, we saw a dog, or we saw a person, or we saw an accident in this particular image frame. If you have a way of doing this on vehicles directly, right, and indexing it in a way that if another vehicle or maybe a pedestrian, wanted to be aware of something that another vehicle saw, you could do that, so sort of in a more expedient way.
Gotcha. Okay.
So that's like one example of a research problem here. But it's just, it's more, so it kind of pushes more on sort of like device discovery kind of issues, right? Because these cars are moving very quickly, and it's like, what rates do you have them beacon at, so that you make sure that if two cars want to form a connection, will you be able to do it in enough time, right? So before the cars move out of range of each other, and you get the data transfer rate through. So it's more of sort of an ad hoc networking paradigm than like, say, streaming video to a laptop that maybe isn't moving around too much in a room. Yeah.
Related to that, like a current feature that I've noticed on Google Maps is they have the speed trap detection. So can you elaborate like a little bit how that relates to it?
Speed trap detection.
Yeah, like I get a notification saying that there's a speed trap, and then like 1 minute later I see a cop.
Yeah. So I know that so Google acquired Waze, and I know Waze. The way that they do the sort of the police detection is it's sort of a crowdsourced thing, right? Where it's like if someone sees a cop, you can basically flag it in the app, and then that gets shared with everybody else that is sort of using the app. So I don't know if right now the cars are sort of autonomously sort of detecting speed traps. I suppose when the Google, so sort of the fleet of Google cars that do the mapping, I suppose that if they were to go through like an intersection, they could see if there was a traffic camera. They could probably, add that to the map. But yeah, I don't know specifically what's going on under the hood there. But yeah. Okay, so then so moving on, so looking kind of into like one of these low power sensors. So I sort of talked about them abstractly. I think. So maybe now people are more familiar with this kind of device. So now, I don't know how many of you have worked with like a Raspberry Pi or an Arduino? Yeah, a good number of you. So this is like a much lower end processor, right, than what you would find in your mobile phone. So some of these low power sensors, they might have only an 8-bit wide data path in the CPU. It might only have 4 kilobytes of RAM. It's going to use a really low power radio for communications. So this might be a radio that's only from 10 to 200 kilobits per second, and obviously Wi-Fi sort of in megabits to gigabits. So the throughput is much lower. They have low power sensors. They can either be battery driven or self powered. So by battery driven, that could be a small rechargeable lithium battery. It could be a pair of AA batteries that you might need to replace once every couple of years, or they could be completely self-powered. And then they have some really small amount of flash storage. So usually the program that you write to one of these things isn't going to be updated very frequently, right? So you might have to do maybe a patch if you have a bug, or maybe you want to change the rate at which they're sensing because, I don't know, maybe the parameters of whatever thing that you're studying has changed. But reprogramming them isn't sort of a common operation. So you write one piece of firmware to them, they sort of do their job in the background and send their data out over a radio. And the data usually consists of sort of time series sensor readings that it collected over time. And so two kind of specific examples. So the Atmel AVR, I think this is like the processor that's actually inside a lot of the Arduinos. Again, it has an 8-bit wide data path, it has 4K of RAM, a little bit of flash. And then there's also this other one that's been used, I think this is more popular now, at least outside of the Arduino space, for embedded sensing. So there's this TI MSP430 that's also powerful. And then if you want more horsepower, right, so the Raspberry Pi actually uses something like an ARM7 or an ARM9, which is sort of like a similar type of processor that you would find in a mobile phone, right? So you can think of it as sort of being on that scale. And I think that there are ways that you can power optimize these into devices that aren't necessarily plugged into the wall. Now a little bit about the low power radios that you find inside these devices, right? So there's so one thing, right? So all of these, like if you really had all degrees of freedom of control, you could probably make something that's sort of more tailored to a particular application that's really energy efficient. But there's this pesky entity out there called the FCC, and they don't let you just use whatever radio frequencies you want. So almost all of the radios that you'll find that are used in these sensing applications are either in the 900 megahertz band or the 2400, so the 2.4 gigahertz band. So, Bluetooth, Zigbee, they're both in 2.4 gigahertz. I think 900 megahertz isn't used as much because their hertz used to be used a lot for like analog systems like baby monitors, I think old cordless phones. There are also, a couple of protocols, so like RFID tags, for example, operate in sort of the 900 megahertz band. And all these different radios, they can have different modulation schemes and protocols. So I know, so Zigbee is sort of just a traditional, so sort of you pick a frequency and you use it, and it has sort of carrier sense mechanisms like you would find in Wi-Fi, where you can avoid, collisions by listening, for the presence of energy from another transmitting radio. But then, like Bluetooth, for example, actually modulates its frequency sort of with each packet, right? So it sort of does this frequency hopping scheme where every packet it sends on a different frequency, and then the order at which it hops across these frequencies is randomized. And so the idea behind that protocol, right, is so if you randomize it enough, like hopefully the likelihood that two senders are on the same channel at the same time is low, right? And then if you do detect a collision, there are sort of built-in ways of sort of revising your hopping schemes so that you could avoid those collisions in the future. And so these radio technologies here are short range. They're usually less than 100 meters. So one emerging radio that isn't on this slide, right? So how many of you have heard about 5G networking? So one of the big things in 5G is basically support for, we have pretty good coverage for cellular communications with phones, and 5G the vision is to bring that to IoT radios, right? So you basically can have a radio and a cell tower that has a range of up to 10 kilometers to talk to these low power devices, right, that don't have a lot of data to send. And then the radios in these devices, right, they're very low power. So I think that, so Wi-Fi radios, when they're transmitting, it can be something like on the order of like a watt of power at maximum. So they do adaptation in Wi-Fi, right, depending on what the range is. So the CC2420 is an example of a Zigbee radio, and the most that it will ever use to transmit is actually 17 milliamps of current, which is a couple of orders of magnitude lower than Wi-Fi. So of course there are coexistence issues here, where if someone is streaming, say they're streaming the new Game of Thrones episode at high definition, and you were operating on the wrong channel with one of these CC2420 radios, if they're sort of operating in the same frequency, maybe the sensor can't get its data through. So there are these other things that you have to consider when you have different types of networks that are operating sort of in the same space. And then the other weird thing is, so sometimes listening can actually take more energy than transmitting, right? So if like the noise floor is very high, right, you have to do like a lot of work to sort of decode the bits that the transmitter sent to you. And that sort of signal processing that's involved in receiving packets, sometimes it's more work to figure out what someone sent to you than just sort of blindly sending something out at some power level, and that costs less than trying to figure it out. All right, so low power sensors. So I mentioned earlier, so they run on batteries. So this was a Telos B mote that was used in wireless sensor networking research. So this was really popular sort of in the mid-2000s. I think there's still some research groups that sort of are actively using this for some applications. Like I know like there's a couple of ongoing deployments that are looking at sort of monitoring the habitats of endangered species. But so sort of the total battery capacity you have here is sort of 2 AA batteries. So the entire system, so this includes the CPU and the radio both being on, is around 25 milliamps of current. And then the expected lifetime, if we were to run this continuously, would only be 4 days. So if you want to get longer lifetimes out of these devices, so you can think of a few different ways of approaching this. So maybe the most naive thing you could do is you could like strap a car battery to this tiny sensor. Of course, then you lose like all of the benefits of having a small sensor. So usually, people working in the space of researchers are creative, and they've looked at ways that you can use energy harvesting, including solar, wind power, maybe even motion, and you can use energy over time to sort of refill a smaller battery, right? So you can get a lot more than 4 days out of them. And then duty cycling, right? So say I mentioned the radio receive circuit earlier, and so the thing that you wouldn't want to do, right, is if no one has any data to transmit, and you were to continuously have your receiver active, right, you would be drawing something like 25 milliamps of current and getting no benefit from it. So usually what these radios do is they do something called duty cycling, where they will wake up periodically to see if anybody has anything to send, and if they don't have anything to send, then they go back to sleep. And there are ways that you can ensure that when you wake up, you'll hear the packet, right? Because basically you can send a very long transmit packet, so when the receiver wakes up, you'll hear part of that packet. So, you're sort of shifting the burden of power, from the receiver to the transmitter, but if you're clever in the ways that you sort of manage this, so overall, throughout the battery-powered network, you can, achieve, something much less than 25 milliamps that's listed there. And then what kind of sensors can you find in these? So I think most of the sensors here now have found their way into mobile phones, but there's sort of a low power equivalent that you could put in one of these small IoT devices. Maybe a couple of different things that might be more specific to a sensor could be maybe humidity isn't something you would find in your phone. I think there's a barometer, but not a humidity sensor. But there's basically, if you want to sense it, there's probably a sensor out there that can record the data for you. So I already touched briefly on this. So self-harvesting sensors. So if you want to avoid having to use a big battery, right, you can actually just harvest energy from the environment to power them. So there's a bunch of different ways that you could do this, from sunlight, from vibration, thermal. So one interesting angle that some researchers have gone after with this is maybe the thing that you're sensing can actually be the thing that's powering your device. So for example, if you want to know temperature and you're harvesting your device from one of these temperature scavenging devices, so sort of the rate at which you are sending packets sort of implicitly says something about how much thermal energy there is in the environment, right? So in some cases, right, it could be that just by harvesting power on your sensor, you can sort of do the sensing sort of for free in the background. All right, so typical design issues that go into this. So if you're only looking, so sort of from the perspective of one device, so basically it's, how do I optimize, how I use different subcomponents of the sensor so that I harvest or use enough energy to meet some lifetime requirement. So maybe you're trying to make the device live forever. If you're harvesting power, you could potentially do that at least until your battery stops being able to recharge. Or it's like you have a budget where it's like, I want the sensor to last for an entire year. How do I get the average power consumption down so that the device won't run out of power until that time is elapsed? Then if we move up to sort of looking at it from the perspective of an entire network of sensors. So there's a lot of opportunities to sort of do optimizations across a network. So for example, you can aggregate data. So the worst way that you could manage one of these networks, right, is if you got a single reading from another sensor, and then you immediately decide to forward that sensor reading, so sort of to the network sync, right? A smarter way to do it is to aggregate data together, right, and basically send all of that data out in one packet. There's a lot of overheads, right, in sending networking packets, so it makes a lot more sense to sort of bundle a bunch of sensor readings, with the header information that you would already be sending for the packet. So duty cycling, I already touched on that. And then there's localization and synchronization. So if you're going to be deploying a large number of sensors, so maybe out in a field, or maybe your application is monitoring if a forest fire is going to happen, right? So because you might not be carefully placing each node, a network of sensors, they need to be able to sort of self-localize, right? So maybe with respect to its neighbors, maybe you equip them with GPS. And then because devices can be intermittently powered, so another challenge in a network is sort of keeping all of the sensors synchronized, right? So it's really hard to extract any meaning out of sensor readings if all of the timestamps are wrong. You don't really know what to do with the data. And then routing, right? So routing in this building, right? I mean, it's a very planned thing, right? Where it's like you assign each device an IP address, and you have a lot of control over how you route data around. But if you don't know how you're going to be deploying these devices out in the wild, they sort of have to figure out a routing table on their own, and then what metric am I going to use to figure out which node that I'm going to route to, right? So maybe you would do it based on packet loss rate, right, to figure out who the best guy is to send your data to. Or maybe you bring into it, something about the remaining battery life on a node, right? So it's like maybe I don't want to transmit data to a sensor that has a battery that's more depleted than the others, right? So maybe even though another sensor sort of has a higher packet loss rate, but it has a lot more battery power, maybe I decide to route to that node instead. So there can be like a lot of different ways that you might want to optimize routing in a sensor network. And then, so then once data is brought out of the network, so say you've managed to get all of this data into the cloud, then there's sort of these big data analytics that you do to provide sort of meaningful insights across all these different sensors that were deployed across a large area. And then the last part of it is sort of making recommendations and sending alerts based on the data that you collected, right? So that's sort of closing the feedback loop. So I guess on a wearable sensor, you could think of this as like, so maybe you're an elder person and you're prone to falling. This would sort of be you're collecting information about how your legs are moving, and then you want to send them an alert, like a warning that like maybe we think that you're going to fall sort of in the next 10 minutes. So that would be an example of sort of sending an alert back to a sensor. You can also think about closing the feedback loop of a large deployment of sensors where maybe you figure out that one particular area sort of may have a sensor anomaly, right? So maybe you see something really interesting that's happening in one geographical part of the network. So maybe you would send a message back to the network telling that group of sensors to sort of sample more frequently, right? So you get more information about an area that has information. All right, so now I'm going to get into sort of some applications of things that you can achieve with these sensors, and then also sort of building on this idea of making the devices themselves energy efficient, right? How can we use sensors to make all of our infrastructure more power efficient, right? So it's like if you really optimize a device that is already only spending 25 milliamps of power, you're not going to be saving that much in sort of like a global warming perspective, right? But if you can sort of use the information that one of these low power sensors provides to maybe save the power that's spent in a 10 megawatt data center, then we're talking about saving a lot more power. So green computing in general, so it's looking at the idea of sustainable IT, and it asks the question, so how do we design energy efficient hardware, software, and computer systems? And so overall, so computing for greening, we're using IT to make physical infrastructure more efficient. And this could range from anything like, in a residential home, this could be using something like a Nest thermostat. In offices, they have much more complex heating and ventilation and air conditioning controls, but there's a lot more opportunity to save power because big buildings use a lot of power. So offices, other buildings, and then transportation, right? So vehicles, like if you can optimize, things like traffic a lot better, right? I mean, you can really, reduce the amount of fossil fuels that cars burn. Yeah. So kind of a historical overview. So energy efficient mobile devices have been it's been a problem where I think over the years it's gotten a little bit better. I mean, it used to be that a mobile phone like a smartphone, you would get sort of less than a day of battery life. Now I think that the standard is maybe you expect a little bit more than a day of battery life from your mobile phone. But the motivation here is different, right? So we're not trying to get better battery life. We're just trying to reduce just sort of the total amount of energy that things use. And so this is like really driven by recent growth in data centers. So data centers use huge amounts of power. So a lot of this is just because of the computation that they're running. There's been a big push to do even things like GPU rendering. So there's like a big announcement from Google a few weeks ago, right, about basically they want to be rendering computer graphics in the cloud. And this is all this is one thing that's like basically causing all these data centers to consume more power doing processing. And then not only do you have to power the processors, you have to power the storage elements, right? So it costs a certain amount of energy, to even write to flash storage. And then to even keep these data centers cool, I think it's around 20% of the energy of a data center just goes towards cooling down the data center from doing all of this computational work. And so the overall goal, right, is to make these data centers more green and have a lower carbon footprint. And then, of course, we can apply greening to other systems. So maybe this extends into heating, ventilation, and air conditioning in buildings, right? So we can think of that as sort of another IT system that we could make more energy efficient. So again, I just mentioned, data centers, so what does one typically, like how can we think about the energy that one of these uses? Well, 20% of the power in a typical office building actually goes towards computing compared to all of the other energy that a building uses. So 50 to 80% of the energy that's used by a large college, so I think this is probably largely driven by, every student has a laptop that they bring to campus, and if you think about all of the energy of all of those laptops and computers and data centers on a college campus, you actually get a number that's 50 to 80% of the energy of a campus is used for computing. And then overall, globally, it's 3% of our carbon footprint, and it's actually growing, right? So as more and more, so say that Google example, right? If we're basically making data centers do more work, and basically more people have computers, more people have mobile phones. So if you sum all of that together, it's going to be even a larger fraction of the global carbon footprint. And then of that 3%, so data centers are actually a pretty large fraction of the overall IT carbon footprint. But PCs and mobile devices, again, are playing a role in this. So has Prashant talked at all about data centers at all in this course yet? So this is just a really brief overview, right? So data center, it houses servers, it houses storage, it houses networking gear, GPU processing. So this is a picture of what a data center looks like in Dallas, Oregon. So it's basically 12 football fields in size. This particular data center has 100,000 servers, and it actually consumes 100 megawatts of power, which is enough power to run a small city. And then, so looking at the amount of money that a data center has cost to run, sort of over the last 30 years, it's actually, gone up quite a bit. And if you look at sort of what the contributors are here, so there's just basically the cost of infrastructure. So that's replacing equipment in data centers. I don't know if the buying real estate is factored into that if you need to build a new data center. So energy cost, right, is actually maybe around like a third or a quarter of like the total cost of ownership. And then like the server cost is like it hasn't really changed that much, right? So even though like the server cost is the same, we're actually using even more energy. And so the overall energy bill of a Google data center, so if we assume we have 100,000 servers, and so then the monthly cost of one server, if we consider it to be sort of a 500-watt server, and then if we think about the cost per kilowatt hour, so if you have an always-on server, its monthly cost is going to be around $50, which might not seem like a lot, but if you have 100,000 servers, that's going to be $5 million a year that you're spending just to keep those servers powered. And then the cost of cooling, so a metric that's commonly used in data centers, it's called the power usage efficiency. And if you had a PUE of 2, that would mean that the cost of running your servers would double because of cooling. So Google actually has a PUE of 1.2%, so that's 20% overhead for cooling, which adds on another $1 million for running this data center for a year. So that's $6 million per year. So even if you don't care about the environment at all, you have sort of a monetary incentive as a company to bring these numbers down so that you can save potentially $6 million a year if you were to get them to run. I guess that would be for no power, but probably do better than $6 million. And then so designing a green data center. So if we could actually take a normal data center and make it green, so the benefits that you get is that you can reduce the cost of running the servers, you can cut the cooling costs, and then you can employ the best green practices for infrastructure. So basically that means like maybe you find ways to recycle components, where it's like if you have slower servers, like maybe you can repurpose them in a lower tier data center for other customers instead of throwing them out. There's a lot of ideas out there on that. And then reducing the cost of servers themselves. So you can build more energy efficient servers by using better hardware. You can use better power supplies. So there's actually some interesting work out of Microsoft research a number of years ago where they had actually looked at powering racks of servers, so basically an entire row of racks of servers. They were looking at powering them from fuel cells. So basically directly generating the power that you need to run the servers, inside the data center itself. So then, like, a couple of the big gains you get there, you don't have to run inside these data centers. It's like, giant bundles of wires in order to carry the amount of power you need to power the servers. Another clever idea too that I saw out was basically, normally we view the heat from a data center as waste, right? And we need to cool that server down, right? So in order to keep it running. So one idea is, okay, there's a lot of places in the world that are cold and we need to heat them. So maybe you can install a server in their house, and like maybe you can run workloads on the server and you can heat their house, and to sort of turn that waste heat into something that can benefit somebody. So of course, if you were to distribute computation around like that, it would be much harder to manage the server infrastructure instead of having it in a data center, but it could maybe help you with cooling. Right, and then you can manage your servers themselves better. So you can be smarter about, when you throttle the CPU speed of different computers, you can turn things completely off, if it's not a time of high workload. And then virtualization, right, can let you move an app, much closer to where the consumer of the app is located, right? So you don't need to spend as much money on, routing the data through network infrastructure. And then, so the thing that I mentioned about, using servers as heaters, so we can also think about, better ways of actually cooling them. There was actually a bunch of work. I think this is so when I was at HP Labs, there was a big push around, doing much smarter thermal engineering of the way that the server racks themselves are constructed, right? So the way that one of these data centers is usually structured, right, is it's basically you have basically two rows of servers where they're both, all of the heat is like pouring into sort of one sort of column, that goes down the data center. And then that, is fed down into the air conditioning system for the data center. And then cold air, is sort of blown, into the front of the rack. And so by doing this, right, so if you do a very careful thermodynamic analysis of the servers, of the racks that you put them in, and then also the building, right, you can actually circulate this air much better and be able to cool them more efficiently. And then, why are we wasting money cooling servers when there are places on Earth that are already cool, where why don't we just put our data centers there, right? So there have been some efforts in putting servers in underground bunkers, right? It's because the ground is pretty cold when you go down far enough. I think it was Google was looking at putting basically containers of servers down under the ocean, which I guess it's probably bad to be warming up the ocean, but maybe you're only doing it a little bit. But it saves Google a lot of money, and you can basically cool a data center for free. And then, another one, right? This is an article from a couple of years ago. So Iceland is actually becoming a popular place to install your data center. So sure, the network latency might be a little higher to talk to a server in Iceland, but you can sleep better at night knowing that your processing is more energy efficient. Yeah, so this is sort of the end of the part of the lecture about sort of green computing. If anyone has any questions about this, I can answer them. If not, I'll move to sort of a special topic thing that I had worked on at Disney Research that involves like home IoT applications. Yeah.
So I just wanted to bring up the cost of manufacturing. I heard about how the solar cells end up costing more, like environmental costs just in manufacturing.
Yeah, so that's one big considerate. Yeah, so there's a lot of debate right now. So if you were to take away sort of these tax incentives to install solar panels, do the economics actually work out where you save more money over time than you spent manufacturing the panel? So I don't know an exact answer to that. I think the answer is yes now. Now that I think the sort of benchmark energy, so sort of conversion efficiency. So basically the amount of energy from the sun that enters the panel, 20% of that energy gets converted into electricity. So with that number, obviously, there's an amount of time that you have to have the panel installed, where so sort of you reach your break-even point, maybe it's like a decade after you've installed the solar panel. And then if you let it run for, like home mortgages are usually like 30 years. If we're talking about a home solar panel, so sort of the first 10 years are spent, paying for the panels, and then the last 20 years are spent, sort of reaping the cost benefits of installing the panels. The other thing with solar panels is they don't work as well over time. I know usually, at least for residential solar, so they usually give you sort of a guarantee where, after 30 years, we guarantee that, I don't know, maybe your panels will still produce 80% of what they produced when you originally bought them. So I mean, it varies from panel to panel and company to company. I'm guessing that probably Tesla probably overclaims because Elon Musk is a little bit, he claims some big things. But but there's a lot of considerations that go into maintaining solar panels. You have to be a lot more careful in the way that you care for them than say, if you're just pumping in energy from the grid. I mean, you basically offloaded your problem, right, to National Grid or whoever your power provider is. But now it's like you're responsible for generating your own power, so you have to be careful about, using it in such a way that it's not going to fail prematurely. All right, so I spent kind of the first part of the talk, so just basically discussing, sensors, and they have batteries, and you have all these limitations, and batteries wear out over time. You have to worry about things like duty cycling and replacing them after a year. So when I was at Disney Research, we had this project around doing battery-free Internet of Things, and the way that we did this was using simple RFID tags as sensors. So RFID tags, right? They don't have batteries. They use a very small capacitor. You probably can't even see it. I think it's maybe this part of the tag right here is the thing that stores power. But what happens, right, is so basically the reader on the left sends like a 900 megahertz signal to the tag, and the tag uses that power to basically charge up its capacitor. And then it's actually able to sort of modulate the signal that the reader send it back to the reader, and then embedded in that signal that it sends back is some information. And so you can think of, maybe you could put like a really, really low power sensor in the RFID tag and sense something like temperature, and then maybe encode that information that you send back to the reader. But it turns out that the physical layer wireless information that the tag generates also has some information sort of implicitly in it. So there's two things that people usually look at, right? So the first is looking at the received signal strength of a tag, which can sort of give you a rough idea of how far away the tag is from the reader. So that gives you information about the course location, right? And then there's sort of this notion of phase, right? So basically, if you look, there's multiple periods of the signal that are being sent out. And so 900 megahertz, so I don't remember the exact numbers off the top of my head, but every wavelength of RF, right, you can basically, if you can do a phase detection at the reader, you can sort of, if you can track how that phase changes over time, and you can unwrap it into something, that varies from period to period of the signal just to sort of an absolute measure of distance, you can actually get, more fine-grained location information than you can get from RSSI. And so the kind of sampling rates that you can get, so these readers send around a watt of data to the tag. The tag consumes, on the order of, microwatts of power. And so sort of, with all of the workload that's present, so they usually achieve around 50 samples per second, right? So basically you can query an RFID tag 50 samples a second when it's, a few meters away from an RFID reader. So, RFID has been talked about a lot for, things related to supply chain management, right? So you have a giant Walmart warehouse, and you want to be able to track, where all of the items are that you have in the warehouse continuously over time and know how your supply chain is operating. So why haven't we seen, these RFID readers sort of move out of, warehouses, into places like homes? Well, there's a few problems with sort of existing RFID readers. So the first is that routing power and communications to readers is challenging. So they actually consume, the readers consume a pretty significant amount of power. It's usually a few watts of power. The tags consume almost nothing, but if you want to instrument an entire building, you have to deploy, a bunch of these readers. The second is that the signal that the tags send back to the readers is very, very weak. So that means that you need to have large antennas with a lot of gain so that you can actually basically decode the thing that the tag is sending you. And the third is that the antennas need line of sight coverage to the tag. So because the signals are weak, if you sort of have a physical barrier between the antenna and the tag, that's usually enough so that the tag itself won't even get a message from the reader. And just so this video here, it's slightly ridiculous. This is basically setting up, so if you wanted to do sort of like a demo RFID deployment, so these are sort of all of the steps that you would need in order to get, so sort of an uninstrumented smart home, turning it into one that is equipped with an RFID reader. In this project, so we looked at how we could reuse existing home infrastructure in order to deploy RFID readers. So you can think of, homes already have things like, this is hard to see, but this is a light bulb, right? So we have like lighting that's already in homes. There's wiring, and power outlets that's already distributed around a home. And we also have networking infrastructure that's already deployed. We can probably reuse a lot of this, right, to make deploying RFID readers much simpler. And so the solution that we had was basically taking everything that you need to run an RFID reader and fit it inside of the form factor of a light bulb. So basically all of the networking, all of the computation, the lighting itself, the reader antenna, if you could fit it all within the confines of a light bulb, you could basically replace a normal light bulb with one of these RFID light bulbs. You already have power, routed to the light socket, and you're basically done. So just in contrast to the previous video, this is what it's like to install our system. So we're just screwing in a light bulb. So how do you use like one of these lighting units to actually, do sort of an interesting IoT sensing type application? Well, so first, obviously you need to install the light bulbs into the home infrastructure, and then you have to associate them with a Wi-Fi access point in your home, right, so that they can, send their data, to a centralized location. So the second is you want to install sort of these tags that I mentioned earlier. So there's places that you might want to sense. You can install them at different places of interest in your home. And then the third is, so when these RFID readers turn on, they're going to be reporting this phase and this RSSI information, and we can interpret this over time, with a back-end server and figure something out about what's happening in the environment. And then maybe I can actuate the lighting itself to give some information, or maybe there's some GUI element that runs on like a tablet or a computer that would tell you something about the home. We'll just quickly show, this is a real thing that we actually built. Has a bunch of components. It has a CPU, it has an RFID reader. It's able to basically be powered directly off of the AC mains. It has basically lighting similar to what you would find in a Philips Hue light bulb, right? So you can actuate the red, the green, and the blue color channels independently to achieve different lighting effects. And then all of this fits inside of a 3D printed housing that's basically the same size as a floodlight. And to think about how you would use this. How does the light bulb perform overall? So if you were to hang one of these, from one of these pendant style lighting sockets from the ceiling, so from the ceiling to the floor, you get sort of that 50 reads per second coverage that I quoted earlier. So that was about 2.5 meters in our setup. And then you can think of sort of the region that you can cover is sort of this cone-shaped region that's described by the 7-meter diameter circle that we projected on the floor. Right. So if you wanted to cover an entire room, you could think of having sort of a grid of these that are deployed throughout a space where you would cover up each of those 7-meter circles by a light bulb. And then so in order to achieve the performance that I mentioned earlier, so one of the things that I mentioned is in order to read one of these tags, you usually need to have a really large antenna. So we sort of get line of sight for free, right? Because we're hanging it from a lighting socket. Obviously, you want line of sight from a lighting unit to a room. You also get this for an antenna. Because the light is small, we actually can't increase the bandwidth that way. So we did some engineering tricks that basically traded off throughput for range, where we ignore some of the RFID channels. So RFID also does frequency hopping, like I mentioned that with Bluetooth earlier. And basically, if we are hopping amongst one of the untuned channels, we just end up discarding the reading. But overall, that lets us get the 50 reads per second, but over like a larger space than if we use sort of a traditional tuning mechanism for the antenna. And then, so to get this whole thing to work, so there are a couple different pieces of software that we had to write. So the first is this server application that sits in sort of a back-end server, and it continuously receives packets from an RFID reader. So what it tells you is So sort of the ID of a tag. So by knowing something about where you deployed the tags, you can basically map that ID that the tag sends you to a location or to an object type. It gives you the RSSI and phase value that I showed you on the first slide. And then it could also send you a sensor value. So one type of tag that we used was actually a temperature sensor, where you can actually stuff a temperature reading directly into one of the RFID readers. And then finally, there's also another server application where the back-end infrastructure will consume these sensor readings, and then it can decide to change the lighting of the lights themselves. And so you can specify sort of an intensity of the lighting channels, and then maybe you want to take a certain amount of time to fade from one light value to another. You can also incorporate that into one of the packets that you send. And so by taking simple RFID tags, so these are all sort of examples of just simple RFID tags, we can think of using them for different types of purposes. So the one on the left, so this is just like a simple RFID tag that's attached to an item, so that those are my keys there. And if we take the ID that those tags generate and we map them to our keys, then if we find this object underneath some reader somewhere, I know that my keys are going to be roughly in that region on the floor that I showed earlier. So a thermostat sensor, so this is actually sort of like a clever hack, where you can see this line here where we've basically cut part of the RFID tag in half. And so what happens is, so this is a mechanical thermostat. So when the thermostat trips, so that part of the tag's antenna actually moves away, and the tag becomes much harder to read. So you can figure out the state of your thermostat at home just by looking at the signal strength that the tag is sending its ID back to the server. So that's how you can build sort of a sensor by exploiting some sort of the mechanical nature of something that you attach it to. So another is related to touch. So again, this was another example where we hacked an RFID tag. We basically cut off part of its antenna. So normally there's sort of an RF tuning that needs to be done between sort of the computer that's inside the RFID tag and then the antenna. And so if you cut off part of the antenna, it's no longer properly tuned. And usually the way these components are tuned is it's tuned with the capacitor that's inside the tag. So if you cut off part of the antenna, so it turns out that the human body actually has a lot of capacitance. And so we used one of these conductive ink pens to actually print sort of a pad where you could put your finger. So this is a tag that won't talk to a reader until you touch it. So you've created a touch sensor out of a normal tag. The fourth, so this is a temperature sensor. So this actually has hardware that's built into the tag itself that can record the temperature of whatever it's attached to, and you can use sort of a special read command to read the sensor value instead of the ID value out of the tag. And then the last, this is like a really simple one. This is a contact switch, where basically you can place a piece of foil over a tag, and so when the foil is covering the tag, it basically acts as a Faraday cage, and you can't read the tag. When the foil is removed, you can read the tag. So you can think of using this on if you want to know if like a door of a cabinet is open, you could put sort of a tag and the corresponding piece of metal on the two parts of the door. Also, it turns out that some home appliances act nicely as like Faraday cages, right? So like washing machines, refrigerators, they're all made out of metal. So if you wanted to read food items when the door is open, you sort of get that automatically right from the tags being inside of something like a fridge. So to showcase the kind of things that you can do if you have sort of an RFID augmented home, there's kind of three different classes of applications that we explored. So the first was navigation. So if you know the topology of where your RFID light bulbs are installed, and then maybe you're wearing a lanyard that has an RFID tag and you know where your items are, you can think of doing things like illuminating lights to guide you towards something that you might be looking for. Or just giving you directions to a particular room, right? Maybe you're not looking for an item, but you know that you want to find out where, you sent a print job to some printer, in an office building, and you want to know where it is, and you could just, tie this system into the printer queuing system, and it could just guide you to wherever your printout went. So the second was infrastructure monitoring. So all of the sensors that I mentioned in the previous, so the tag sensors that I mentioned in the previous slide can be used to monitor sort of the state of our homes, right? So when is our heating system on? You can figure that out with the thermostat tag. You can figure out what temperature a room is with the temperature tag. You can figure out, things related to energy efficiency of a home by if you, instrumented, windows and doors with some of the contact switches, right? You could do that, using the sensor tags. And then the last is prepackaged content. So this is basically content that actuates the lights, right? So you could think of examples where it's like, maybe you have a, I don't think people buy CDs anymore, but you buy a CD. So say you do, and it has an RFID tag inside the cover, right? So maybe it has like some lighting pattern or something that would sync your music up to the light that's installed in the ceiling. I'll show another example of this in a video shortly. These are 3 sort of different applications we thought of that we could use to do this. So the first that I'm going to go over is this application of navigation. This is my former coworker at Disney, and it turns out that he's lost his keys. And so you can see there, right, so he pressed a picture of his keys in the app on his phone. And so because the light knew that the keys were under them, it flashed to guide him there. This one's a little bit more complicated because we needed to use 2 lights. It turns out he also lost his backpack. And so then when he approaches, under this light, I think it stops. And then, oh, there's my backpack. It's right over there. He's had a bad day. So then the next one, so this is an example of basically just doing infrastructure monitoring. So this is showing how we can detect that this drawer is opening and closing, based on that RFID tag being blocked by the metal counter. This is an example. It might be hard to see here, but you can see that the thermostat was detected when it switched. This is a contact switch that was embedded in a door frame, where we can see when someone leaves or enters a room. And then, so that's it for that video. So that's just kind of showing, how each of those sensors works sort of in the context of an infrastructure monitoring application. And then the last is this prepackaged content example that I mentioned earlier. So this is actually a children's storybook, something that like Disney might actually make, where you can actually encode the color values of like different scenes in the book, directly into the pages of the book itself, right? So each of the tags on a page, gets blocked by one of these pieces of foil, and when you turn the page, it knows to like change the light. And then you saw that there is an example of the touch sensor there, where sort of like, in a pop-up book, you can modify part of the book. So there is a picture of like a lightning bolt, touches it, and the light flashes.
Are you the actor reading the book?
Yeah, I was. We didn't have a big budget for
So
yeah.
for the example of the thermostat,
Yeah.
basically the linear movement of the RFID determines how far away the RFID is?
Well, no, so in that case, we actually cut the tag.
Okay.
So so inside of a mechanical thermostat, so there's actually a mechanical part of the thermostat that moves.
Right.
So when you move that metal away from the RFID antenna, basically the performance of it gets worse.
Yes, so
Yeah.
what resolution can you detect?
Oh, that's just binary. I mean, we didn't. I would imagine it's not that good.
Right.
So we just used it, just for a binary classification between, is the heating on or off.
Okay.
I wouldn't trust that you could use it to like
Sure.
do better than that. So that's all that I had for you today. So just a quick summary of what I talked about. So basically, we can make computing, IoT infrastructure more health efficient, and all of these IoT sensors that are out there have there's big opportunities to use them for health applications, and basically the design of energy efficient hardware and software is making this all possible, right? So by using better hardware in more intelligent ways, we can use this stuff for new applications. The second, so using computation itself for greening, so we can monitor IoT or monitor IT infrastructure, and then we can control the way that it's used to save power. And we can use intelligent software to manage the power of the IT infrastructure over time. I don't think I actually talked about this third one, but that would be you can basically use. I think I did mention it. So basically, looking at weather forecasts, right, to decide how you're going to use resources. And then kind of emerging IoT technologies. There's other ones out there. So 5G is one of the big ones that I didn't go into depth here. So I just talked about how you could use battery-free RFID tags, so sort of as sensors, right? If you were able to put readers, throughout a home. So that's all that I had for the lecture today. I think we have that worked out well, 2 minutes. So if anyone has any questions, I can answer them.
So in terms of, I guess, energy efficiency,
Yeah.
we're talking about the reading, sensing
Yeah.
is much more energy intensive potentially than the sending.
Yeah.
what would be, like, is there a comparison for the RFID sensor and reader versus, say, just having two Bluetooth devices or something like that?
Right.
What
So
would be the benefit? Like, is there
Yeah.
a green benefit to
This is-
actually using the
yeah.
RFID sensor?
there would be a green benefit if you had enough RFID sensors, right? Because you know the RFID reader probably consumes 4 or 5 orders of magnitude more power than a tag. Yeah, I mean, so if you were to leave that RFID reader running all the time, you would need to have thousands of RFID tags in order to drive the average power consumption down. So we built that sort of as just like a research project, so we didn't do sort of any duty cycling of the light bulb itself, but you could think of using maybe another proximity sensor or something, or motion sensor, where maybe you would trigger actually turning on the RFID reader part by having some other low power sensor. So that's like a trick that's played a lot in these systems, where you'll have sort of a hierarchy of sensors, where you'll have like a low power sensor that's used to activate a higher power sensor. So that could be like like some of these battery powered surveillance cameras, right, have motion detectors, and then they're only going to capture like a picture or video when someone is in the frame.
I was curious, like, with a technical question, when you were going back to, there's a little diagram of different components of that, like, experimental light bulb that you built.
Yeah.
I was wondering if it's, because I noticed there was, like, little fans in there.
Oh, yeah.
Interesting. I was
So-
wondering if that's a normal thing, like if
It is
the
not a
tube
normal
lights
thing.
do that, or if it was just this is like, you're building something for testing.
Yeah, we were building, so none of the people that designed that were thermal engineers. So we actually had to run the LEDs, like if we ran them at higher than a 50% duty cycle, the thing would burn out, after a few hours. So there's a lot of energy consuming components in there, right? So you have the LEDs themselves, you have the driver circuits, right, that actually drive the LEDs, those consume power. You have we were using an Intel Edison computer, which basically, I think it was a high-end ARM, no, it was the Atom processor, right, which I don't think exists anymore. So it was an Atom processor and a Wi-Fi and a Wi-Fi radio, and then also an RFID reader that takes a few watts of power. So it's like if you're consuming that much power inside of a small space, our solution was to put fans in there and have baffles and try and vent the heat out of the light bulb. But yeah, that is something that you wouldn't find in sort of a traditional smart light.
And that's probably why you demoed it with like the single string hill.
Yeah, because you had better cooling. Yeah. All right, great. I guess that's it. So thanks everybody for coming.